Okay, just to show this, you might think surely there is a tree data structure in C++, similar to how there was a stack and a queue in the C++ standard library. Found include stack, found include forward list for the singly linked list, found include queue, found includes double-ended queue, and so on. So we saw not tree, but X tree. Maybe it's like a mutant tree, like the X-Men. So if we type tree, we see X tree is here. And if we found include it and run this program, just so that I can open it up over here in the tree view, what I often call the tree view. So X tree, if only I know the alphabet. X tree, okay, there is a macro pound define standard. So we see tree, okay, tree consisting of these value types and traits. Let's open one of these up. Let's see. So tree, and we have node left and right, and something called scary. So that's interesting. This code is blocked out at the moment because I'm not running on C++ 2023. We would need to. Okay, let's not get into that. The default is C++ 14 on this computer. So we see left and right, and we see nodes. That's the only thing I'm trying to get at here. So left and right kind of implies that this X tree is binary, only consisting of two children nodes at most. Can we make objects here? Using our usual notation. Is there a constructor for X tree? These are good questions. We're going to write our own tree class though. So you might imagine that we are going to use templates again, so that we can have nodes consisting of strings and objects and all sorts of stuff, whatever we like, most anything that we like, characters, strings in this case, and characters in this case, and integers in the case of the thing called a binary search tree that I just looked up. Binary search trees are generally going to consist of integers. So we're using templates here. And we need a node. And I'm going to emphasize that is a node of a tree by saying tree node. For the linked list, we just called it. And for the queue, we just called it node. And I think we used a struct. I guess I'll just keep it as a class here. And we have, I'm using public. I'm looking at my slides, obviously. So we have a node value. So the value in the node, which is the value 4 here and the value 2 here. So the data of interest, just like we've done with linked lists. So T node value, tree node of type T, and a pointer, so left, and a pointer to the right child. So this is a binary tree. If you want, you could use a vector of type tree node of type T. I think this syntax works correctly. And if you want a general tree, a tree that could mimic an operating system file hierarchy consisting of an arbitrary number of children, but we're going to keep it simple for now. And also binary trees are maybe regarded as more commonly used than general trees. Again, general trees consist of any number of children nodes that you like. Okay. So maybe it's valuable to look at this picture at this point. So this is a binary tree, and we have a left pointer to a left child node, and we have a right pointer that contains the address of the node of the right child, and A is the data of interest in this case. And in this case, this ground, what electricians would probably call a ground symbol, this means null, points to the null pointer, because the G node containing the value G has no child. It's kind of interesting to think about the fact that a doubly linked list also had links to two nodes, which we call previous and next. So that's not the same as left and right. It's just an interesting observation. Okay, so we have a constructor function definition, a default constructor, which I'm just leaving empty, which is potentially not a good idea. That it'll be okay. We take tree node const t ampersand and a node value to start with. This is the root contents. So the value that we pass in here is it would be the value 4 in this case, it would be the value 40 in this case, and whatever the value of the root node is. That's what we are probably referring to here. Because when we create the tree, we're going to create its root node first. Okay, so these are my member variables. Let me emphasize that with a comment. Member functions, because I've made everything public. Member variables. Okay. So this is my constructor. Nothing exciting going on here. I am using this. So this is the address of the current node. So that suggests that I might be creating a tree node object of type, whatever the type is, and calling it root. And I pass in a parameter here, which is the node value, and maybe I start with the value 3. So that is, let me just take this example here, start with the value 4. So now I have a single node containing the value 4, and it has no left and right at the moment, but I'm going to add a left and right in a bit so that this becomes a tree consisting of more than just a single node. But we'll get to that in a bit. Let me stick with the order of my slides. Maybe we're interested in determining whether or not a particular node is a leaf. So if we'll write is leaf, and we don't necessarily need to pass in a parameter here, because this is a member function and it has access to node value and, more importantly, left and right. These pointers to tree node objects. So we could say if left equal null pointer and right equal null pointer, return true, else return false. So in this case, I haven't explicitly initialized these to the null pointer, but what is root arrow left or root dot left? The member variable. And what is root dot right? What are these initialized to? And we'll just run it all. So null pointer. So this makes some sense because root, I haven't declared any, I haven't set root dot left equal to anything yet. So now if we say cout standard bool alpha, to print true and false instead of 0 and 1, and we say root dot is leaf, we should see that this is indeed a leaf because it has no children at the moment. So that is true. Okay. Hopefully that definition is straightforward. Okay, uninitialized, maybe we should explicitly initialize these to null pointer. I think maybe I did this for no linked list. And now the node value is uninitialized, but yeah, that's okay. Probably fine. Are we still seeing the same outputs here? Yes. Okay, so pose the question, what code could we write in main to build this tree? Tree with the root node value 1 and left child contains the value 2 and right child contains the value 3. When we think about that. So we'll want to change this to a 1 and no particular need to print these things, though we might want to print this later. So we have access to left and right. And we can update this. Maybe we say equal new tree node of type int. And this left is a pointer type, as you can see, the asterisk. And as you can see by the way we defined it up there, we set root.left equal to, remember, new returns a memory address. So this should work. We're expecting a pointer. And the value that we pass in here to the constructor function, not the copy constructor, that's what that is, not the default constructor. Excuse me, that's the copy constructor right there. That's the move constructor, and that's what we wrote right there. So the node contents, that's if we're wanting to generate this tree, the left child needs to contain the value 2. So 2. Root dot right equal new tree node int 3. We don't have to use this dynamic memory allocation. We could say tree node int pointer to it called left child of root and use the construct. Left child of root takes the value, left was 2. And instead of saying root.left equal new tree node int 2, you could instead That's one way to do this. Remember, new is slower than heap memory allocation is actually slower than static memory allocation. But instead, what we could say is root.left equal the address of left child of root. We could do both of these. Now, if we say is root a leaf, it shouldn't be. Now the left child of root has no children, so it should be a leaf. So false and true is what we should see here. Yes, so false and true. Root has a left child and a right child. So this function, the isLeaf function, will return left is not null pointer and right is not null pointer, so we'll return false there. But the left child of root has no children. So you get the point of how building a tree is going to work. It's not particularly glamorous using this approach, and maybe a person would think that there's a more clever way to write this code, and I'm sure there is. But we could build arbitrarily complicated binary trees. We could build a larger binary tree in a similar way to what I've written so far. The root of this tree contains the value A. The left node, the left child of root contains the value B, and the right child contains the value C, as you can see here, and so on. And it gets a little silly seeming if your tree has a certain depth, especially the node H, but it makes sense. The node H, you would say root, arrow right, arrow left, equal new tree node containing the value H. And that is what I just said the same thing as this code is saying, unless I made a speech out. Yeah, so this is a bit of text I snipped from a textbook published in 2002. The definition is not very glamorous. And I mentioned the song by Fergie. Okay. I mentioned this Fibonacci tree. I think I'm not going to get into it this semester, so maybe later. Okay. So we haven't talked about tree traversal yet. We will, and I will also talk a bit about general trees. And I quite enjoyed making this, writing this code. It mimics the process of creating new folders and new files on an operating system. So whenever I did do what I just did there, how is it that it happened? A primitive way to do it could be using this code that I'm skipping through here very quickly. An in-array tree node, not a binary tree node, but an in-array tree node. And then there's this add child file, and the file object is a type that I defined. I'm not going to ask students this semester to do anything similar to this, but I might in the future. So a file consists of a name and a date modified. And I'm taking that from here. So there's a name and a date modified Windows Explorer software. So children links. A vector of tree nodes of type T, pointers to those. So the code gets fairly fun. So I have a create file node function that creates a pointer to a new node of type in-array tree node. And what is this in-array tree node? Have I already mentioned? Yeah. Here's my class declaration and member variables. So for the binary tree node earlier, I had a left child and a left link and a right link. So we could prompt the user for a file or folder name and the date modified and read these in, and then we could create a file object and return new node and new node. Okay, that creates the root node of that's similar to creating a top file here, like a new folder and new folder name. And now this add child file would take a new folder name as it would take the node to that as its argument. It's been a while since I've looked at this, of course, so, but yeah, this code worked whenever I played with it last semester. You might be curious to run with this idea, but for the sake of this semester, and typically the content in a data structures course does not get into n-array tree nodes or general trees. I'm saying n-array because the nodes can consist of any number of children, as in n, like the variable name that's often used in mathematics to indicate an arbitrary number of things, n. Okay, but in the next video, we're going to get into tree traversal algorithms, and also we will talk about what it means to be a binary search tree. So here's the algorithm for the level order traversal. Level order traversal is probably the way a human would read it, and then we'll do in order traversal, which is actually a recursive function, which is neat. And we'll do some testing. We'll create trees and traverse the trees and see if the in-order traversal prints is indeed in this thing called an in-order traversal, which I give an example of here. And we'll write a couple of different functions for some algorithms for tree data structures before we move on to the binary search tree, which is a special type of binary tree that has some nice uses. And write a couple more, one more algorithm, maybe the most complicated algorithm for trees to get the depth or the level of a particular node. Like in this case, the level of the node containing the value 64 is 0, 1, 2, 3 if we use zero-based counting. So that's another interesting algorithm. Okay, but we'll talk about that in the next video. So far, we've done this. We've created a simple binary tree consisting of the nodes 1, 2, and 3.